Kia ora Year 9. This video is for students who are finding the work on linear patterns really easy. I wanted to give you something a little bit more challenging and quite fun to do. So this video is on what we call quadratic patterns. I'm going to do two things in this video. I'm going to show you how to work out when a pattern is quadratic, and then I'm going to show you how to find the rule for the nth term. And the examples I'm using are from the fabulous Dr. Austin Maths website, and they're the worksheet that I've given some of you in class already. So this is just the first half of the worksheet. I'm probably not going to get through all of these, but by the end of this video, I want you to be confident with being able to use the method that I'm going to show you. So let's start out by looking at a graph, because I want to give you the idea of what a quadratic pattern is. So we haven't done much on graphing yet, but I think some of you have already done your own work on graphing. Let's think about if we've got a linear pattern with toothpicks. We've got the first pattern, the second pattern, the third pattern, and the fourth pattern. Well, the reason that we call it a linear pattern is that when we put it onto a graph, it forms a straight line. For example, if I had this pattern here, we can see that between those toothpick patterns, we get 2 extra toothpicks every time, right? And we can write the coordinates of that linear pattern like this. And then we can stick them onto our graph. And you see that they form a straight line. So my first one is here at 1, 3. The next one's at 2, 5. Then at 3, 7. I don't know why I picked odd numbers. That was a bit stupid. Then we take our ruler and we can join up a straight line. And we're going to do some more work on that later on in term 2. But not all patterns are like that. And the pattern that I've drawn in GeoGebra with the blue dots is what we call a quadratic pattern. And quadratic comes from the Latin word for square, which is, I think it's quadratus. And in this one, what we've got is we've got the pattern number here, and we've got our pattern number squared here. So 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. And you can see that you can't put a straight line through there because the gap from one to the next is getting bigger in quite a special way as we keep going, right? And that's the key to finding the rule in these problems. If you look at how big the change is from the first to the second one here, it's 3. And then between the next two patterns, the difference is 5, and then it's 7. And if we kept going, we'd see that that pattern was 9. So you can see that we've got a pattern in the differences. And we're going to use that to identify that we've got a quadratic pattern. So we call that the first difference. And it's a bit like being on a treasure hunt. Like if we see that the first difference has got a pattern like this, we look at the second difference. And here the second difference, so the difference between the differences, is 2 here, 2 here, and 2 here. And once you see that you've got a constant second difference, you've hit the jackpot. You know that you've got a quadratic pattern. Now, the proof for all of this, for why it works, is a bit too hard to show you guys in a video in Year 9, but I might be able to do that with some of you in class if we get time. But for now, all I want you to get is the idea that if we look at the first difference and we find that it's not constant, that tells me that it's not a linear pattern, right? So one more time. Then we look at the second difference. And if the second difference is constant, then that tells me that it's some kind of quadratic pattern. So we're going to start out with just a few of those, and then we'll get some different types of quadratic patterns going. What I think you should do when you've got just a sequence of numbers like this is start off by always putting them into a table. So for this first one, we've got 8, 11, 16, and 23. Write that as the first pattern, the second pattern, the third pattern, and the fourth pattern. Now, the first step is to identify that it's not a linear pattern, and you can see that the gaps are not constant. Now we try the second difference. So we go like this. So 5 take away 3 gives me 2, 7 take away 5 gives me 2. And you can see that we've got this constant second difference. Now, what I want you to do next is to take that number, take the second difference, which is 2, and divide it in 2. That's going to tell me how steep a quadratic pattern I've got. And all of these first ones that we do in this worksheet are going to give me a constant difference of 2. So let's just erase a little bit of this. I'll take out some of this mess. the constant second difference is 2, we're going to try working out a rule that's got n squared in it. So in this column, I'm going to work out what is n squared. Well, it's going to give me 1, 4, 9, and 16. So that's kind of the start of my rule, but you can see that that's not quite right because I want to have 8 toothpicks here, but I've only got 1. So the leftover is 8 take away 1, which is 7. In the second pattern, I want to have 11 toothpicks, but an n squared rule is just going to give me 4. So we're 7 off again. And you can see that in this pretty simple case, what I've got is an n squared column and then a leftover every time of 7. So putting those two things together, we can try out this rule. T is equal to n squared plus 7. So let's just check that it works. 1 squared plus 7 is equal to 1 plus 7, which is 8. 2 squared plus 7 gives me what I want, which is 11. 3 squared plus 7 gives me 16. And 4 squared plus 7 equals 23. Okay, so that's our first one done. I'm going to pause the video back on the screen now, and I want you to try out the next two on your own. So I'll hit pause on recording, and you can hit pause on the video, and I want you to do in your books, try these two. So do a table, figure out the second difference, figure out the n squared part, and then work out the leftover. All right, so here's what my working looked like for the next one. This is my pattern number. This is my toothpick number. Well, actually, toothpicks doesn't really make sense here, right? So just think of this more abstractly as just a sequence of numbers now. Okay, so first we're identifying that we haven't got a linear pattern because here we've gone up by 3, here we've gone up by 5, and here we've gone up by 7. So it's not linear. We check the second difference, and we find that it's constant and it's 2. So we halve that number as our trial rule, and we say, well, it's going to be something with n squared. Now, this step from here to here is a mystery black box that's going to stay like that for a little while, right? I haven't shown you why that works, and I don't like that I haven't shown you why it works, but I just haven't. So off we go with figuring out our n squared. So n squared, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. I'm just going to clean some of this up to make this a little bit clearer. All right, so there's my n squared column. Ugh, this is getting messy. Let's see. Where are we? There's my n squared column. And now we've got my leftover column. Well, my leftover column is -4, take away 1, which is -5. -1 take away 4, also -5. 4 take away 9, also -5. And 11 take away 16, which is -5. So that means that my rule here will be t is equal to n squared minus 5. And we can test that out just with a couple of them. 3 squared is 9. 9 take away 5 gives me 4. So it looks pretty good. 2 squared is 4. 4 take away 5 gives me -1. So that's that one done. The next one has got nicer numbers. No one loves working with negative numbers and patterns. You've got to be a bit careful. Let's try this next one. What have we got? Well, we've got 1, 2, 3, 4 for my pattern number. 6, 12, 22, 36. Right, so the first difference is not constant, so it's not a linear pattern. Now the second difference here is constant, but it's not 2, right? It's 4. So what we have to do for this one is a little bit more interesting. We have to halve that number. So my test pattern this time is going to have 2n squared, right? 2 times the number squared. So we have 2 times 1 squared, which is 2. 2 times 2 squared, which is 8. 2 times 3 squared, which is 18. And 2 times 4 squared, which is 32. And now we do the leftover. And let's see what we get. Well, we get 6 take away 2, which is 4, 12 take away 8, which is 4, 22 take away 18, which is 4, and 36 take away 32, which is 4. So my rule here is t is equal to 2n squared plus 4. All right, this video is 10 minutes already, so I'm just going to pick out a couple more to do. And I want to pick out a harder one. So let's see. Which one? What did we just do? We did the 6, 12, 18. So we've done this one. You can keep playing with those other ones, but I want to go down to this second batch of questions to show you some more fun, interesting ones. So the one that I'm going to look at first is this one here, which is 2, 7, 14, and 23. So this is kind of the next level up. We've got good at finding the second difference, and we've got good at halving that number. But in the ones we did up here, they were all patterns like n squared plus 5 or 2n squared minus 3, right? In these ones, the leftover is going to be its own little pattern. So let's try this. We've got n here and t here. N is 1, 2, 3, 4. T is 2, 7, 14, and 23. Right, so off we go as usual. 5 here, 7 here, 9 here. First difference is not constant. The second difference, whoops, is not 3. 7 take away 5 is not 3, guys. 7 take away 5 is 2. Okay, so my second difference is constant, and it's a nice, easy 2. That means that my test rule is going to be n squared. Right, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. Now, what about this leftover? Well, 1 minus 1 is, no, not 1 minus 1. For my leftover, I'm looking at the term and I'm looking at the n squared. So 2 minus 1 is equal to 1. 7 minus 4 is equal to 3. Oh, 14 minus 9 is equal to 5. And 23 minus 16 is equal to 7. So what we've got here is a little bit different. You can see that the leftover is not a constant. The leftover is its own little linear pattern. Right, now if you're watching this video and you've got this far through, I figure that you're pretty good at doing linear patterns by now. So we should be able to see that the leftover rule is 2n minus 1. And so to get my overall rule for t, I take the n squared part and I take the leftover part and I add them together. So my rule here will be t is equal to n squared plus 2n minus 1. And we can check that out. For example, when n is 4, we should get 23. Let's see if we do. Well, n squared is 16 plus 2 times 4 minus 1. That gives me 16 plus 8 minus 1, which is 23. So it's always worth checking, especially when you're starting out with these, that it actually does work by putting in a value of n and checking. All right, so that's all from me now. I wonder if I should give you the answers to some of those just so you can check them. I think I will. So if you pause the video again, I'm just going to pop up the answers for a couple of those sequences. Where are we? This one here, C, will give you 2n squared plus 3n plus 4. The one before it, B, was the one that we just did, and that gives you t is equal to n squared plus 2n minus 1. A in here is equal to n squared plus n plus 1. Now, I think that that is as far as I went because it is Sunday night and I need to get to sleep before school in the morning. So I'll give you the other answers in class or we can work them out together. Thanks for watching and I will see some of you tomorrow.